Namaste dosto. Imagine you're watching a cricket ball gently rolling to the crease, getting closer and closer to the wicket without actually hitting it. Just like that, in mathematics, we study what happens to a function as the input approaches a particular value. This is what we call a limit. Today, we're diving into limits of trigonometric functions like sine, cosine, and tangent to understand their behavior as the angle approaches some value. Now, why do we need this? Sometimes, simply plugging in the value of x doesn't work, often because it gives indeterminate forms like 0 divided by 0. These tricky forms need a little algebraic magic or clever identities to simplify. Figuring out these limits is not just a neat exercise, it's crucial when we deal with derivatives, especially for periodic functions like sine and cosine. Our key focus today will be on limits where x approaches 0. And remember, x is always in radians here. More on that later. For example, we'll be looking at limits like sine of x over x as x tends to 0 and many others around this special point. To visualize, picture the graph of sine of x and the curve of sine of x divided by x near 0. Notice how both approach the y value of 1 as x gets closer to 0. Exciting, right? So let's begin exploring these intriguing trigonometric limits together. Let's jump straight into the most famous limit in trigonometry, the limit of sine x divided by x as x approaches 0. This one is a cornerstone for many other results. It equals exactly 1. In simple words, as the angle x gets closer and closer to 0, the value of sine x over x moves smoothly toward 1. How do we know this? There are geometric arguments using the unit circle. Imagine a circle with radius 1. If you mark an angle x in radians, the length of the arc that subtends this angle is exactly x. Comparing this arc length with the sine of x, represented by the vertical height of a point on the circle, gives us a beautiful inequality that sandwiches sine x over x between two very close values, eventually proving the limit is 1. Important to remember, this only holds true when x is measured in radians. If you use degrees instead of radians, this fundamental limit does not apply. This limit is super useful when differentiating functions like sine x or when dealing with limits that initially look like 0 divided by 0. So, keep this classic limit close to your heart. Limit as x approaches 0 of sine x over x equals 1. It's a key that will open many doors in calculus and trigonometry. Next up, let's examine the limit of tangent x divided by x as x approaches 0. At first glance, tangent can be tricky because it's sine over cosine, and cosine can zero out at places, giving vertical asymptotes. But near 0, cosine of 0 is exactly 1, making things easier. We use the identity tangent x equals sine x divided by cosine x to rewrite our expression as sine x over x times 1 over cosine x. Now, as x approaches 0, the limit of sine x over x is 1. We already saw that. Also, the limit of 1 over cosine x becomes 1, since cosine 0 is 1. Multiplying these limits together, 1 times 1 equals 1. So the limit of tangent x over x as x tends to 0 is also 1. This confirms the continuity of tangent function near 0. Just a peaceful, smooth curve around this point before it swings wildly near its vertical asymptotes at plus and minus pi over 2. A quick note. This works because cosine x is not 0 near 0. So dividing by cosine x is valid. So, remember, limit as x approaches 0 of tangent x over x equals 1. Another essential tool for your trigonometric toolbox. Now, let's tackle a slightly different limit. The limit of 1 minus cosine x divided by x as x approaches 0. Direct substitution gives 0 over 0, classic indeterminate form. But all is not lost. We use the trigonometric identity 1 minus cosine x equals 2 times sine squared of x over 2. This transformation helps us rewrite the original expression as 2 times sine squared of x over 2 divided by x. As x approaches 0, sine of x over 2 behaves like x over 2, because sine theta over theta tends to 1 near 0. Putting this all together, the whole expression tends to 0. This limit appears in proofs when finding derivatives of cosine x, and it helps simplify nested limits involving 1 minus cosine x. Whether you rationalize or substitute, these algebraic simplifications clear the 0 by 0 hurdle smoothly. So, the key takeaway: limit as x approaches 0 of 1 minus cosine x over x equals 0. Easy when you know the identity. Sometimes, the angle inside sine or cosine isn't just x, but a multiple, say times x or another constant. To handle these, we use substitution. For example, for the limit of sine of ax divided by bx as x approaches 0, set theta equals a times x. This means x equals theta over a. We rewrite the limit as sine theta divided by b times theta over a. Rearranging gives us a over b times sine theta over theta. Now, as theta approaches 0, sine theta over theta approaches 1, our standard limit. So, the entire limit simplifies neatly to a over b. This substitution technique is a powerful way to bring complex-looking trigonometric limits back to familiar territory. It's especially handy when you see constant multiples inside the trig functions. Keep this handy method in mind to simplify your limit problems systematically. Let's put our substitution into action with a quick example. Evaluate the limit as x approaches 0 of sine of 3x divided by 5x. This fits our previous pattern, sine of ax over bx, whereas 3 and b is 5. We let theta equal 3x, so x equals theta over 3. Substituting, sine 3x becomes sine theta, and 5x is 5 times theta over 3. Rearranged, that's sine theta over 5 theta divided by 3, or 3/5 times sine theta over theta. As theta tends to 0, sine theta over theta tends to 1. Therefore, the limit is 3/5 times 1, which is 3/5. Shabash. You just applied substitution to crack a limit question. Remember, the answer is 3/5. Ready for a challenge? Let's evaluate the limit as x approaches 0 of tangent 5x divided by sine 3x. Direct substitution gives 0 over 0, indeterminate again. First, rewrite tangent 5x as sine 5x divided by cosine 5x. So, the expression becomes sine 5x over cosine 5x times 1 over sine 3x. Group it as sine 5x over sine 3x times 1 over cosine 5x. Using our standard limits, sine 5x over 5x tends to 1 and sine 3x over 3x tends to 1. Multiplying numerator and denominator by x to use these limits, the expression transforms approximately into 5x over 3x times 1 over cosine 5x. The x terms cancel, leaving 5 over 3 times 1 over cosine 0, and cosine 0 is 1. So the limit becomes 5/3. Excellent. You simplified it step by step by breaking down tangent and applying known limits. Keep practicing such decompositions to master tricky limits. Let's wrap up what we learned today about limits of trigonometric functions. Remember these formulas. First, limit as x approaches 0 of sine x over x equals 1. Second, limit as x approaches 0 of tangent x over x equals 1. Third, limit as x approaches 0 of 1 minus cosine x over x equals 0. The secret to resolving tricky limits is to use these identities and substitution methods skillfully. Always make sure your angles are in radians. Substituting degrees instead invalidates these beautiful results. And whenever you face 0 divided by 0, try rationalization or algebraic simplification to untangle the indeterminate forms. I hope this clears the fog around trigonometric limits. They're foundational for understanding calculus and beyond. For practice, think about this. What's the limit as x tends to 0 of sine 2x over 4x?